is one-dimensional time-dependent heat transfer. The physics hasn't changed. It is Fourier's heat transfer law, which in one dimension states that the heat flow rate equals minus K times the spatial derivative of temperature, where K is the thermal conductivity constant of the material. We also need to know the relationship between temperature and heat energy, which is heat energy equals C times volume times temperature, where C is heat capacity in joules per unit volume degree K. When we use this equation, we will rearrange it to get temperature equals 1 over C times heat energy per unit volume. The model for 1D time-dependent heat transfer is the time derivative of temperature equals K over C times the second order derivative of temperature with respect to X, and we'll derive it now. Consider the heat flow into a small control volume, the section of a one-dimensional wire from X to X plus dx at time t. The flow rate into the control volume at X is Q of t comma X. The flow rate out of the control volume at X plus dx is Q of t comma X plus dx. So we negate that to get the flow rate into the control volume at X plus dx. And so the total heat flow rate into the control volume is Q of t comma X minus Q of t comma X plus dx. Temperature in the control volume equals 1 over C times the heat energy per unit volume in the control volume. So the time derivative of temperature in the control volume equals 1 over C times the time derivative of heat energy in the control volume per unit volume. The heat flow rate into the control volume is the time derivative of heat energy in the control volume. And we divide that by dx to get the time derivative of heat energy per unit volume, and we have the first half of equation 1. Now we use Fourier's heat transfer law to write the heat flow rate as K times the partial derivative of temperature with respect to X evaluated at t comma X plus dx minus K times the partial derivative of temperature with respect to X evaluated at t comma X. And we have the second half of equation 1. Taking the limit as dx approaches 0, we have the partial derivative of temperature with respect to time equals K over C times the second partial derivative of temperature with respect to X, and that's our model for time-dependent 1D heat transfer. Now we will consider the same process as in the first video with a 4-meter wire held at a constant 20 degrees at the left end and a constant 100 degrees at the right. But we won't assume that the wire has reached a steady state, and we'll see what happens to the temperatures at the interior points as time progresses. This begs the question, what are the temperature values at the grid points 2, 3, and 4 when the process starts? That is, what is the initial state of the system? This is up to us to specify as we like, and we'll specify that T2 equals T3 equals T4 equals 0 at time T1, which is 0. First, we substitute for the derivatives in the model. The substitution for the first order time derivative is the usual Euler substitution, appearing on the left side of the equal sign in equation 1. And the substitution for the second order spatial derivative is the same substitution used in the previous lesson, with the difference that we include the time variable in the time-dependent formulation. So the equation is the temperature at time Tn plus 1 xi minus the temperature at time Tn xi divided by dt equals K over C times the temperature at Tn xi plus 1 minus 2 times the temperature at Tn xi plus the temperature at Tn xi minus 1, all divided by dx squared. That's equation 1. We rewrite that equation in index notation as equation 2. Note that in this notation, the index of the time variable now appears as a superscript. When we write the program to compute the temperature values, which is coming shortly, we will store them in a one-dimensional array T. We will initialize T with the initial state of the system and then do time stepping to advance the solution in time. That is, we'll compute the temperatures for time T2 and store them in the T array, and then compute the temperatures for time T3, store them in the array, and so on. We won't save the past values of temperature as time progresses. So, besides being more compact, the index notation corresponds very closely to the MATLAB code used for the computations. Solving equation 2 for t superscript n plus 1I gives us equation 3, which is t superscript n plus 1I equals t superscript ni plus k times dt divided by c times dx squared times t superscript n I plus 1 minus 2 t superscript n I plus t superscript n I minus 1. And that's the computational equation that we'll use to compute solutions to this problem. Now we're ready to get busy. This is what the calculations look like when done by hand. I suggest you pause the video for a bit and study them to make sure you are comfortable with them. Now we have the program itself. Let's go over it line by line. Nx equals 5 sets the number of x grid points. N equals 10 sets the number of time steps. We initialize the temperature array to all zeros and set dx to 1 and dt to 1. We initialize the left boundary value to 20 and the right boundary value to 100. The next line creates an array of grid point coordinates for use in the plot statements that follow. The plot statement graphs the initial temperature profile. We will plot the temperature profile at each time step on the same graph, so we have the whole statement. Now we get to the actual computing. The for loop is the time stepping loop. We save the values for the nth time step before computing the values for the n plus first time step, and we'll see why in a second. The next for statement sequences through the interior grid points only, so the index variable goes from 2 to nx minus 1. The next statement is the computational equation verbatim. Note that only temperature values for time step n can be used on the right side of the equal sign. That is why we save them 2 statements back. After computing the temperatures for the n plus first time step, we graph the temperature profile and then on to the next time step. Finally, we turn the whole statement off so we can start afresh the next time we run the program. And this is the result showing the initial temperature profile and a series of profiles as the temperatures increase in the wire approaching the steady state straight line between 20 and 100. Now we want to add a time-varying heat source to the model. The heat source supplies heat energy to the wire measured in watts and is represented by a function f of time and position. The units of heat energy applied to a one-dimensional volume are watts per meter. So the rate of heat energy supplied to the control volume is f of t comma x times dx. Recall that the time derivative of temperature in the control volume equals 1 over c times the heat flow rate per unit volume. The heat source adds to the heat flow rate per unit volume, and the amount it adds is f of t comma x times dx, the heat flow rate, divided by dx, the volume, which evaluates to f of t comma x. So the heat source adds 1 over c times f of t comma x to the time derivative of temperature, and the differential equation including the heat source is the time derivative of temperature equals k over c times the second partial derivative of temperature with respect to x plus 1 over c times f of t comma x. So let's do an example with a heat source. We start with a wire of length 10 held at 0 degrees at the left and right ends and heated over its entire length by a constant heat source Ft, x equals 10 watts per meter at every position, and it's constant in time. We use a grid spacing of dx equals 1 and a time subinterval of dt equals 1, and we initialize the wire at 0 degrees K overall. The constants are K divided by C equals 0.3 and 1 divided by C equals 0.5. So we have the model equation as before and the computational equation. And so let's have a look at what the program looks like. And here's the program. It looks almost identical to the previous program, but the heat source is hiding there somewhere. Try to find it. It took me a moment or two. This is the resulting graph. This example is identical to the previous one, except that the right boundary condition is that the wire is insulated, so that no energy is flowing in or out of the wire at the right endpoint. This corresponds to a Neumann boundary condition that the spatial derivative of temperature equals 0 at the right boundary. Since the spatial derivative is 0, no energy is flowing in or out at the right boundary. The computational equation is T11 equals T10, and it needs to be placed after the loop that computes the values for the interior grid points, because for the n+1 time step, the value assigned to T11 must be the value just computed for T10. So this will add one line to the program. The three types of commonly used boundary conditions are Dirichlet boundary conditions, Neumann boundary conditions, and Robin boundary conditions. Dirichlet boundary conditions are used to specify the value of a variable on the boundary. Neumann boundary conditions are used to specify the value of the spatial derivative of a variable on the boundary. Robin boundary conditions are used to specify a linear relationship between the value of a variable and its spatial derivative on a boundary. A Robin boundary condition thus has the form A times the partial derivative of temperature, in our case with respect to x, plus B times the value of temperature on the boundary equals C. So the computational equation for this boundary condition on the left boundary would take the form A times T2 minus T1 divided by dx plus B times T1 equals C. And on the right boundary would take the form A times T and x minus T and x minus 1 divided by dx plus B times T and x equals C on the right boundary. For example, suppose there is heat transfer to the environment on the right boundary equal to the difference between the ambient temperature, Tm, and the wire temperature at the right boundary, Tnx, and the rate is R times that difference. The rate of energy flow into the right boundary equals the rate of energy flow out, so we have R times Tmb minus T11 equals minus K times the partial derivative of temperature with respect to x evaluated at the right boundary. So substituting for the partial derivative of t with respect to x at the boundary, we have on the right side of the equation minus K times T11 minus T10 divided by dx, and we can rewrite this equation to get a computational equation for T11. So the assignment is to reproduce the three results in the video And then a fourth problem, which is to modify the third so that on the right boundary the wire has a Robin boundary condition as specified, and some of the code for that problem follows, along with the graph showing the results.